Okay, so one search algorithm we have seen till now is the linear search, where in an unsorted array, if you want to search for a given element, we start from the first element and keep searching for the element by comparing the search element one by one with all the elements till we either exhaust the array or we find the search element. The second way or the second algorithm that we look into is called as binary search. Now, binary search takes a little lesser number of comparisons to find out if the element is present in the list or array or not, but with one condition that the given list or array has to be sorted already. Okay. For example, let's say I have this element, which is this list, which is available to me. It is in sorted order, in ascending order. These are the positions of the items. So zeroth position is 10, first position is 20, so on and so forth till fifth position is 60. I'm searching for the element 50 inside this. So in binary search, what we do, instead of starting for the search of element from the beginning of my array, I will start from the middle point. I will find out where is the middle point of this array, find the index value of that, and then start searching from there. So for example, in this case, my leftmost position is 0. My leftmost position here is 0. Rightmost position is 5. Right. So, right. Now, if I take found to find the middle point of these two, I can take 0 plus 5 by 2. So my middle point in between these two will be 0 plus 5 divided by 2, right? Now this is going to be decimal value 2.5. We can round it off to 2. So saying the midpoint of these five elements would be the second element, right? Now let us take 50 and compare it with 30. Obviously, these two are not equal. But second inference we can draw from this is 50 being greater than 30, and because this array is already sorted, the number 50 cannot lie on the left hand side, right? That means the number 50, if it is present in the array, has to be present in one of these three numbers. That means the midpoint is not equal to the search element, and because 50 is greater than 30, the 50 can only be present in one of these three numbers and not in these three. So we are automatically finding out that these two elements cannot be equal to 50 even without comparing it. Right? So we don't need to compare here at all because it is already sorted, and we have found out that 50 is not equal to 30 and the number 30 is less than 50. So these two cannot be equal to 50 in any way. So now our search array becomes this. Right? So we have to search for 50 among these three now. Right? So now our leftmost element becomes 3. So in the new array, leftmost element is the third element of the array, rightmost element is the fifth element. How did we come to 3? Just take this 2, add 1 to it. Whatever the midpoint we got here, go to the next element. Fine. 3 and rightmost element is 5. Here the midpoint is 5 plus 3 by 2, which is going to be 4. Right? Now look at the fourth element. Fourth element is 50. Search element is 50. 50 is equal to 50. So we can find out that this 50 is present in it at the position 4. Right? So now we just only compared twice. We compared with 30, we compared with 50, and we could find out that 50 is present. Fine. So please remember with the assumption that the array is sorted. Binary search would not work if the array is not sorted. Right? Now let's repeat this for a different number. Let's say I want to search for the number 20. Right? So let me copy this in a new set. Right? Now I am searching for the number 20. Right? So we'll again start with the left being equal to 0, the right being equal to 5. The mid would come to same 2. Okay, 0 plus 5 by 2, 2.5, 2.5 rounded off to 2. So now we'll compare 20 with 30. We can see 30 is bigger than 20. Right? 30 is not equal to 20 and it is bigger. So it being bigger we can deduce that the 20 number cannot lie on the right hand side of this midpoint, right? So whatever midpoint we found out, that number is greater than the item being searched for. So 20 has to lie on the left hand side of 30. So our search should not include these anymore. Our search should include only these two numbers, right? So let's pick these two numbers now and restart our search. So this becomes the search element. Left remains at the leftmost being 0. Right, we will move towards we'll move the rightmost element to the left of the midpoint because we know the element lies on the left of the midpoint. Our midpoint was 2, reduce the right by 1. So right becomes equal to 1. So now mid will be equal to 0 plus 1 by 1, which is going to be 0. 0.5, which is going to be 0. Now mid is 0, that is this element. So 20 comes here. We are going to search for 20 in this. 20 is not equal to 10, right? Now if 20 is not equal to 10, that means we have still not found the element, but we can also see that 20 is greater than 10. So if the element is present in the array, it has to lie on the right hand side, right? So now again we'll on the right hand side we only have one number in this example, right? So we'll again restart by shifting the left of our array by incrementing mid by 1. We'll left as 1, right will remain as it is, and midpoint will become 1 plus 1 by 2, it will become 1. So we'll take 20 here, and the search element also is 20, and we'll compare these two. 20 is equal to 20, so we have found the element, right? So two examples we saw. First example, when the element was on the right hand side, where we changed our left starting point. Second example, when the element was on the left hand side, where we changed the right starting point of the array. Let's take a third example when the element is not present at all. So I have same array. Let's say I'm searching for the element 90, right? So we'll again start with the same concept, left being 0, right being 5. The mid value will be 2. So 2 is 30. I'm comparing 90 with 30. 90 is not equal to 30 and 90 is greater than 30. So the item can, if 90 exists in this array, has to lie in this range. So let's see if it is present there. 40, 50, 60 is taken. So our left moves from 0 to position 3, one more than the midpoint. So left will be made as 3, right will be made as remain as 5. Our midpoint will become equal to 5 plus 3 by 2, which is 4. So fourth element is actually 50. We are looking for 90. 90 is not equal to 50 and 90 is greater than 50, so it has to lie on the right hand side. So again we have to move towards the right of the midpoint. So left will again be equal to 1 greater than the element 5. Right will be equal to 5 and mid will be 5. So now we have got 60 here and we are comparing with 90. 90 is not equal to 60, right? Still item not found. Now, how do we know that we have exhausted all the possibilities? To reach that conclusion, now let us say we have found out that 90 is greater than 60. So the algorithm will assume if 90 exists, it has to exist on the right of this 60 element, right? So I have to move towards the right. That means if I have to move towards the right, I have to increase left. That means left will become equal to 6 and right will become equal to remain at 5. Now once the element of 6 left becomes greater than the right, that means we have crossed all the elements. As soon as the right left becomes greater than right, that means we have finished the searching in the array. That means we have started from here, our left has exceeded the right. Right is still pointing here. I have left has crossed the boundary of the elements present. Fine. So that means can't search for the elements any further. The element 90 cannot be present. So the stop condition for this searching of binary search is whenever the left becomes greater than right, we have to stop. So keep searching as long as left is less than right or equal to right. Both conditions are okay. We can keep on searching. Once the left becomes greater than right, our search has to stop and decide that the element being searched for is not present in the given array. Okay. That's the basic binary search algorithm. So let's try to put this into our Python programming. Right. So we have defined a function called as binary search. It takes a list as a parameter and the item being searched for as a parameter. We're starting with left as 0. We're starting with right as the length of the list minus 1. Now why minus 1? Because length of list is 6 elements. Fine. But when you say length of list, I'll give 6. But the index value is 5. Right? Because you're starting from 0. So it will be 6 minus 1, 5. So left is 0, right is 5. Start a while loop. Continue the while loop as long as the value of left is greater than less than right or equal to right. As long as one of these two conditions is satisfied, you keep looping through this. Each time we enter the loop, we calculate the mid value as left plus right divided by 2. Please note the double mm, division operator here. If I remember, this is the floor operator. It reduces to the nearest int of rounds off to the lower integer value, right? So we find out the mid. Compare if the item being searched for is it equal to the mid number present at the mid index. So is it equal to num list of mid? If it is equal, we have found the element. We can return at which index did we find the element. If this is not equal, we have to move towards the right of the mid or left of the mid value. So that is decided depending on compare the search element with the middle element. So for example, if you look at this, we were searching for 50. We compared 50 with 30. After doing this comparison, we found out that 50 is not equal to 30. So this comparison turned out to be false. So we are not going to return anything. Instead of that, we are going to move towards the right or left. So the comparison told us this that search item is greater than the mid item. So search item is not less than the middle item, but greater. So if it is not lesser, it has to be greater. So we'll come here and change the left index to mid plus 1. All right. So left becomes equal to mid plus 1. So left becomes whatever mid value plus 1, it becomes 3. And restart. Again find the middle value. So 3 plus 5 by 2, 4, and compare if the fourth index element is equal to item, so on and so forth, till you reach a value where left becomes greater than right. So if you are exiting this while loop without returning any value, that means you found out that nowhere in this list this item is present, right? That means if the item is not present, you have to return a minus 1 to indicate that you did not find the item that you're looking for. So to run this algorithm, we're just taking a simple sorted array and item being searched for is put here. I'm receiving the index value of where the element was found and calling the binary search, passing the list, passing the search item. If the return value is minus 1, we can print the item was not found, else we can print where the item was found. Right? So let's just run it and see what it prints. So you can see element 2 was found at index 1, which is the correct value. Right? I can change something else. I can say which element I can search for index element number 6. Element 6 was found at index 5. If I give a number which is not present in this, it can say it was not found. Fine. So you can see the number of comparisons will drastically reduce in this as compared to our linear search, but only limitation being that the item, the list has to be already in the sorted order. Otherwise, it will not be able to proceed in this fashion because if it's not sorted, we cannot use the logic of moving the left and right based on the middle value, right? So if you derive the complexity of this algorithm, you will get to value of log of n. That is number of comparisons required for your binary search algorithm varies as the logarithmic value of n. It's not proportional to n directly, but it varies as a log of n, which is much smaller than direct proportionality of with n. Right? So that's the binary search algorithm. Hope the concept is clear. Uh, Thank you.